한다고요? Okay, I think we can start. So it's my great pleasure to introduce Masafumi Hattori, who's going to talk about boundedness and moduli spaces of K-stable Calabi Yau fibrations over curves.
Thank you for introduction and the invitation. It's my great pleasure to talk here. Today, I'd like to explain our work on boundedness and moduli spaces of K-stable Calabi Yau fibrations over curves, which is a joint work with Kenta Hashizume. Today's talk consists of two contents. The first one is on adiabatic stability of Calabi Yau fibrations over curves. I think there are many experts, but let me explain the history of K-stability and the evolution of its criteria for K-stability. And next, I'd like to explain our criterion for uniform adiabatic stability of cavity tropical fibrations over curves. Adiabatic stability is stability of fibrations when the polarization are infinitely close to the amplitude bundles on the base. And yeah, so indeed we showed that before the K-stability of Calabi Yau fibrations over curves can be detected by the K-stability of the base. Precisely speaking, it's a log twisted K-stability, which is some generalization of twisted K-stability. Is a log version from the diagram. Okay, so next, I'd like to explain the construction of moduli of uniform adiabatic stable Calabi Yau fibrations over curves by using our criterion. But before stating this, I'd like to explain the history of GIT and the evolution of K-moduli theory for canonically polarized pairs, low Calabi Yau pairs, and low Fano pairs. Finally, I'd like to explain our construction of adiabatic. Sorry. Dead.
Move the mouse on your computer.
Okay. Dead. Excuse me. Sorry. So I'd like to explain our construction of adiabatic K-moduli and some boundedness of Calabi Yau fibrations over curves, and I'd like to explain its boundedness application on K-stability. I mean, by uniformity of K-stability is I mean that yeah. So adiabatic K-stability is the K-stability of the Calabi Yau fibrations when the polarizations are infinitely close to the base. So there is a problem that I mean, for families. So I mean, we can make all K-stable tropical fibrations. Cavity tropical fibrations, which is uniformly adiabatically K-stable. We can make all of them simultaneously uniformly K-stable or not. So we want to answer this question. So let's start. So so there is one of the most important problems in K geometry to characterize the existence condition of a constant scalar curvature K metric on the polarized variety. And it looks like a so analytic problem. But Oban and Yau show that for canonically polarized Keller manifolds, there exists a unique Keller Einstein metric. And Yau shows that for Calabi Yau varieties, there exists a unique Keller Einstein metric. And the Keller Einstein metric is one of the specialization of C-sigma metric. I mean, for canonically polarized varieties and Calabi Yau varieties, C-sigma problem was completely solved. But for Fano manifolds and other polarized varieties, the problem becomes much more complicated. Indeed, Matsushima shows that by using the Matsushima's obstruction, I mean, Fano manifold with a Keller Einstein metric has a reductive automorphism group. So, but blow up of P2 has a 1-point blow up of P2 has a non-reductive automorphism group. So this has no Keller Einstein metric. So there are Fano manifolds with no Keller Einstein metric and a Keller Einstein metric. So to solve this question, Tian first introduced the K-stability for Fano varieties, and Donaldson modified the definition of K-stability and generalized for other type polarized varieties. And they predict the following YTD conjecture. YTD conjecture predicts that K-pole stability coincides with the existence of a C-sigma metric. I mean, in other words, the existence of a C-sigma metric is a purely algebraic condition. Would be a algebraic geometric condition due to this conjecture. And this conjecture was firstly solved by Chen Donaldson and Tian independently for Fano manifolds. But for other polarized varieties, this conjecture has not been solved yet. But if this conjecture would hold, then I think it would be important to detect K-stability. K-stability for concrete varieties, but but to detect the K-stability has still been hard in general. I mean, so to state, before stating the definition of test operation, before stating the definition of K-stability, we have to introduce the notion of test operation. Test operation means K L for polarized variety XL is a normal proper and geometric variant family over P1 with 1 and infinity fiber coincide with XL. And in particular, the infinity fiber coincides with XL with the trivial GM action. And the K L amplitude line bundle. And due to the intersection formula by 1 and Odaka, if dimension x equal to n, the Donaldson stack invariant can be interpreted the following n+1 dimensional intersection number. And next, Regime and Jacobi introduce the following analog of Donaldson stack invariant to show the their own regime-utility conjecture on J stability. I mean, this can be also denoted as the following n+1 dimensional intersection number. And here, this overline means the direct closure of H is a equivalent bundle. Anyway, we can finally define K-stability. XL is K-stable if the Donaldson stack invariant is non-negative for any test operation, and uniformly K-stable if the there is a positive epsilon such that the Donaldson stack invariant can be bounded from below by epsilon times the minimum norm. Here the minimum norm is a J functional, and this is a non-negative functional, and it is called norm in the sense that this value vanishes if and only if this is a trivial J map. This is a trivial test operation with J action, with trivial J action. So I mean the uniform K-stability implies K-semi stability. I mean this is a weakest condition, and it is well known that the Donaldson stack invariant. I mean, precisely speaking, the March functional, which is a precise modification of the Donaldson stack invariant, can be decomposed into the non-Archimedean entropy plus JKX non-Archimedean energy. And it is well known that the non-Archimedean entropy is closely related to the singularities and log discrepancies, as we explained below. But from this formula, I mean, the Donaldson stack invariant is J stability. I mean, J stability can be defined in a similar way as the K stability is also important for K stability, since this functional appears in the Donaldson stack invariant. Okay, and let me recall briefly the singularities and the relationship between log K-stability and singularities. Here, log K-stability is the K-stability of a log pair, which is generalized by Odaka and Sun. Yeah, we can define in the same way by using the log Donaldson stack invariant. Anyway, let x delta be a log pair and the sigma be a resolution of singularity with f a prime divisor on y. And then the log discrepancy of x delta with respect to f is coefficient of this divisor with respect to f. And x delta is commutative terminal if the log discrepancy is positive for any f, and the log canonical is non-negative for any f. And to define the delta invariant below, we have to introduce the log canonical threshold as this. I mean, x delta plus dt, we take the supremum of t, where the x delta plus dt is log canonical, where d is an effective Q-quantity divisor. And Odaka shows that there is a relationship between K-stability and singularities in the minimum model program sense. I mean, let x delta L be a price deminormal pair, and if this means this is an analog of Calabi Yau pairs, and this is an analog of this is a chemical polarized pairs, and so there uniformly K-stable. But we put the KFT condition on Calabi Yau pairs, and he also shows that K-semi stability puts the restoration on singularities in the minimum model program sense. I mean, K-semi stability implies similar canonicity on x delta. Anyway, the K-stability and the singularities and birational geometry are closely related in this sense. But for Fano varieties or log Fano pairs, the criterion problem is much more complicated as a complex differential side. But Fujita and Odaka introduced the M-basis type divisor of the following. I mean, this is a average of a basis of sections, and Fujita and Odaka introduced this as the limit supremum of the infimum of LCTX delta D, where D runs over M-basis type divisors. But Brown and Johnson later showed that limit supremum appearing in the definition of delta invariant is indeed the limit. And they also showed that by making use of Fujita and Lee's variative criterion for K-stability of log pairs. I mean, they showed that the delta invariant is bigger than 1 if and only if the log pair is uniformly K-stable. But Liu Shuzhuan later showed that the condition that the delta invariant is bigger than 1 if and only if the K-stability, the original K-stability of the log pair. And delta invariant is at least 1 if and only if the log pair is K-stable. So log pairs, canonically polarized pairs, and log-canonical pair pairs, they're useful criteria for K-stability. But unfortunately, there are few criteria for K-stability with when K plus delta is not on the line. I mean, not on the line generated by L. So we want to discuss this case. Anyway, Kira geometers has been studied statistic problems on fibrations, and Fine first showed that some morphism of polarized manifolds, and if the base and all fibers have a unique statistic metrics, then the statistic metric exists in sigma epsilon A plus F=L for sufficiently small epsilon. But this is a weakest form. Yeah. I mean, the point is that statistic metric exists in this polarization. I mean, the polarization with polarization sufficiently close to the base. And later, Davan and Sexton and Oge generalized this theorem, and they make use of so-called adiabatic limit argument. This is denoted in the Fine's paper. And I named after them that uniform adiabatic K-stability, the new notion. Let F be a morphism of polarized varieties, and F is called uniformly adiabatically K-stable if there exists two positive constants, such that for any positive constant epsilon smaller than epsilon 0, the Johnson stacking invariant can be bounded from below by the minimum norm times delta, this delta, for any test operation for x epsilon A plus F=L. I mean, original adiabatic K-stability should be defined as a K-stability when the polarizations are infinitely close to the base. But uniform adiabatic K-stability needs a new condition. New condition is the Johnson stack invariant can be bounded from below delta times minimum norm, uniformly independent from the choices of polarizations, which is infinitely close to the base. So it's called uniformly adiabatically K-stable. And for this, I'd like to explain I mean, how do you say? I want to explain the results on Kela geometry. Previous results on CSK problems on Calabi Yau fibrations, but specializing elliptic surfaces. I mean, let F be a polarized smooth variety, a smooth elliptic surface. If kappa x equal to 0, it is now trivial that x at with the Kepler isometric, since the Yau's theorem. And if kappa x equal to 1, x epsilon h plus f+L has a CSK metric for sufficient small epsilon by Janson, Kirsten, and Dierfeld, and so on. Indeed, this shows that this theorem for smooth minimal models. Smooth minimal model means smooth manifolds with net canonical bundles. But if for elliptic surface case, if kappa x to equal minus infinity, it has been not completed yet.
So here you don't assume fibers are smooth, right?
No.
So only the total spaces.
Total spaces are KLT, I will explain that later. This uniform adiabatic stability can be completely detected into by the log-twisted K stability, which is closely related to the generalized row pair. We use the discriminant and Ambrose canonical bundle formula. Okay, so we want to mainly deal with the K stability and CSK problem of the case when kappa x equal to minus infinity. And for specializing elliptic surfaces, for rational surfaces, uniform adiabatic K stability of rational surfaces and K stability of the base. The K stability of the base means row-twisted K stability, which is a generalization of the twisted K stability of diagram, are the same. And next, I'd like to explain the generalization of generalization to the all uniformly KLT to fibrations over curves. So next, I'd like to explain the criterion for Calabi fibrations over curves and criterion for adiabatic K stability, uniform adiabatic K stability. Let's start. To state our criterion, we have to introduce the following new notion of. This is only a sufficient condition for K stability. This is so-called special K stability. Let x delta L be a polarized KLT pair, and we set H as the delta invariant times L plus K plus delta, and if H is ample and there is a positive epsilon, such that for any p-dimensional subvariety, so this inequality holds for any p-dimensional subvariety independently from epsilon. Then x delta L is uniformly K-stable, and say that this specially K-stable. Anyway, this relies on a useful criterion for J stability. J stability is introduced by Regime and Jacqueline to solve the it solves the solution of J equation. And they conjecture the analog for K stability and YTD conjecture for J stability holds. And Gao Chen shows that there exists a useful criteria for J stability, and they are equivalent to the existence of solution of J equation and something like J stability, U for J stability. But they assumed that uniform J positivity, and Data and Pingali solved the this condition can be replaced with the original J positivity, which is a stronger condition than this. And some showed that for any other Keller manifolds. So this is something like the criteria for J stability. And in dimension 2 case, the surface cases, we can solve this by using only algebraic way. And the second ingredient is this inequality. This inequality was discovered by Wilson Johnson and Keveja in the complex setting. And I also showed this in other way. So they are the useful criteria. And this is a generalization of K-stable pairs. Indeed, we choose L to be the minus Ks minus delta. Then the delta, if this is a uniformly K-stable open pair, then the delta invariant is bigger than 1. So this one is so delta invariant is win against Kx plus delta. So this is ample, and then we can solve this trivially. So special K stability contains a lot of classes. In fact, chemically polarized pairs, K-stable Calabi Yau pairs, and K-stable open pairs, K-stable minimal models, and we will later show that uniformly adiabatically K-stable K-stable fibrations over curves are all specially K-stable. But there is a counterexample K-stable rule surfaces. Counterexample. Okay. And next, let's recall the fundamental notion of K-stable fibrations over curves. Let F be a polarized K-stable fibration over a smooth curve if X is control terminal, F is the contraction. This is a Stein factorization of itself, and Kx is a pullback of the baseline bundle. And we can define B as follows, which is so-called discriminant. So this contains the information of fibers. Whatever fibers bad. And we can define M, the moduli divisor, so that the following canonical formula holds. And Ambro shows that M is always semi-ample, and Fujino and Gongyos generalized this fact for LC trivial fibrations, which is LC trivial fibrations. Okay, we assume the base is a curve. By using them, we can state our main criterion for uniform adiabatic stability for cavity trivial fibrations over curves. F is uniformly adiabatically K-stable if and only if the, I mean, this is a restatement of the longitudinal K-stability. C D plus BL is K-stable for general D in M. I mean, M is a sample, so we can take a general divisor by Bertini. And F is uniformly, furthermore, sufficiently small epsilon, they are specially K-stable. And there is the opposite direction result. I mean, if the base is K unstable, then the pair is also K unstable for sufficiently small epsilon. And I'd like to briefly explain the idea to show the theorem when kappa x to equal minus infinity. I mean, then the kappa x equal to minus infinity, the base is a log fun pair for any general D. And this is a technical call, but we can show that the limit of delta invariant of the total space converges to the delta invariant of the base. And if the log fun pair is K-stable, then the delta invariant of the base is sufficiently big. And note that Kx equals to minus f+L. So combining them and by easy calculation, we can check directly special K-stability for sufficiently small epsilon by using our criterion. And for opposite direction, we can show this by applying MMP, by comparing the Donson-Otaki invariance of the total space and the test coefficients of the total space and the test coefficient of the base space. I mean, anyway, this is an easy criterion since K-stability of curves is easy to detect, as Chidi pointed out. Yeah, and by using our criteria for rational substitutes, we can classify all uniform adiabatic K-stability of rational substitutes. I mean, let F be a rational substitute, and it is well known that if X has a multiple fiber, then this is unique. So I mean, we can define the index of X as the multiplicity of the unique multiple fiber of MI tap, or if there's no multiple fiber, then we can define the index to be 1. Anyway, by applying our criteria, XH is uniformly adiabatically K-stable if and only if one of the following holds. I mean, M equal 1 and X has at most released fibers, M equal 2 and X has no 2-star or 3-star fiber, M equal 3 and X has no 2-star fiber, or M is bigger than 3. So, I mean, for rational substitutes and for other Calabi pairs, they depend on what fibers have. Okay, so, and Kevin-chan showed that the YTD conjecture holds for special case stability. So, by using this result, we can deduce also the existence of C metrics in an adiabatic sense. Okay, by using our criteria, we want to construct the moduli of them. But before stating this, I'd like to explain the history of GIT and K moduli. Yeah. So first, to show GIT stability, I mean, asymptotic chance stability and asymptotic Hilbert stability for polarized variety is often difficult. And K stability is an infinite dimensional analog of GIT stability, but unfortunately, GIT stability does not coincide with K stability in general. I mean, Horan and Shepard-Barron shows that there exists several canonically polarized varieties which is a K-stable, but which is not, which is Chow unstable, which is asymptotically Hilbert unstable. And Odaka shows that there is a K-ample overfold that is asymptotically Chow unstable. And indeed, so there are many great contributions to, for example, Heiko-Makanashu, Fujino, Watch-Patak-Fari, Patak-Hsu. Anyway, so, and Kora. So, so there is a projective cost moduli for all K-ample SLC varieties. And anyway, this module was constructed by MMP instead. But by replacing with GIT stability with K stability, Odaka projects the following in his 2010 Kyoto Symposium proceeding. There is a projective cost moduli space parameterizing polarized K polystable pairs with fixed some numerical data. But by Odaka's criterion for chemically polarized pairs K stability, which is that K SBA moduli is one of K moduli spaces. And his conjecture was also motivated by the work of Schumacher, which called. Okay. His conjecture was also motivated by the work of Schumacher. I mean, they constructed, they constructed some CSC manifolds, but not rational or unirational. But
I don't understand why it's cost moduli, not good moduli.
So 2010, in 2010, there is notion, I think, but you doesn't know. But Yuji doesn't know, I think.
But
he knows?
He referred to the good moduli.
I'm sorry. I'm sorry. Okay. Yeah. So it must be good moduli. Is run from upper?
Yeah.
Ah, okay. So sorry.
He learned
Sorry, my fault.
something from.
Okay. Sorry, it's my fault. Anyway. His conjecture was also motivated by the work of Schumacher, and they strengthened the Laban and Naumann strengthened that there is a moduli space. Moduli space means something like analytic space, parameterizing project manifolds with unique C schematics, and all proper subspaces of this moduli are projected by using the positivity of the generalized Peterson matrix. Anyway, I'd like to explain the evolution for K-moduli theory for long pairs. There are many great contributions, but they show that finally they show that there exists a projective cost moduli, good moduli space parameterizing K polystable long pairs, and so there is many techniques, but so there is the delta invariant. In other words, useful criterion for K stability plays an important role. And for Calabi Yau pairs, K stability and K polystability are the same by Odaka's result, but So I mean, such moduli are not proper. For example, the moduli of elliptic curves. But this constructed in many cases. I mean, by using something like a period mapping theory. Anyway, let's recall the history of GAT moduli of rational surfaces. If rational F surface X has a section S, we can construct the components of fibers not passing through S. And we call this surface the rational values of fibration. And Miranda constructed the modular space of rational values of fibration by applying GIT. He realized that GIT stability of them coincides with what fibers they have. For example, they have only reduced fibers. If and only if they are GIT stable. But by our criteria, they have only reduced fibers if and only if adiabatically stable. Anyway, Miranda shows that by applying GIT for weighted projective spaces, parameterizing coefficients of rational wire source forms, and he obtains that there is a quasi-projective closed GIT moduli of rational wire source fibration with fixed section. And I mean that, yeah, so there is a compactification by using GIT. And the Sarah also shows that later there is a quasi-projective closed GIT moduli of all rational wire surfaces with only reduced fibers or MIN type fibers. But we saw that there are uniformly adiabatically K-stable rational wave surfaces not contained in the moduli of cellular. In addition, there is a related result. So there is this result will appear on the tomorrow talk of the OD. But uniform adiabatic stability of rational surfaces implies the straight GIT stability of the corresponding half-wave spaces. So by using the GIT stability of half-wave spaces, there is a similar moduli parameterizing broader rational surfaces than the Serra's one. And
so here you don't assume there exists a section, right?
No section.
So it's not widespread.
No. So it's only the pencil. It's only the pencil's GIT. Anyway, so there are two questions. The first one is, does it exist a separated post moduli parameterizing any relatively polarized uniformly adiabatically K-stable Calabi Yau fibrations over curves? If we succeed at this, we can construct the moduli spaces bigger than the Serra's one. And if it would exist, in the first part of this talk, as I said, could all members be specially K-stable simultaneously by making use of making the polarizations infinitely close to the baseline bundles for any member. So for last 15 minutes, I'd like to explain them. So there are recipes for K moduli for construction for uniformly K-stable Fano fields. So there are three steps. Main steps. There are three main steps. The first one is the boundedness. There is finitely many varieties parameterizing all K-stable objects or not. In Fano cases, changing first shows this boundedness, and later Shu and Juan show that this boundedness by only using the Heiko-Makana-Shields result. And the second one is openness. Openness means for Q-Gorenstein deformations of Fano pairs, the locus parameterizing K-stable objects is open or not. In Fano case, Bragg-Liu showed that this question for uniformly K-stable ones, and later Bragg-Liu showed that locus parameterizing K-semi-stable ones is open. And the third one is this coincides with the separated variety criterion for separatedness of Dreamer photos modular stacks. For F and F prime families over the same curve, suppose that over the punctured curves, they are the same. If the two central fibers are K-stable, then F and F prime are the same or not. This problem was solved by Bram and Shu. Anyway, so this is the goal of this talk. By using an expressed criterion for uniform adiabatic K-stability, we construct a separated Dream-manifold modular stack parameterizing all polarized uniformly adiabatically K-stable trivial fibrations over curves. In other words, for uniform adiabatic K-stability, can be solved three recipes for constructing modular spaces. The most technical part is to show boundedness. Since we have to bound fibrations with only relative data. Uniform adiabatic K-stability is a relative condition over the curve over KLT fibrations. So we have to make the polarization infinitely close to the base. And to answer our second question, we want to bound KLT to fibration. Second question means we can make all families, especially K-stable simultaneously or not. So we want to bound KLT to fibrations XA to CL with relative amplitude divisors A, whose fiber volumes bounded from above. So we do not assume volume A to be bounded. It's frankly speaking, if the polarizations are very infinitely close to the base, so they are wall crossing or not, the modular changes or not, this is a problem. Anyway, the first, we dealt with separatedness. Separatedness for special K-stability immediately follows from the minimization, which is solved by Calabi Yau and canonically polarized pairs and Lofan pairs. And this is a Shim minimization for special K-stability. Let pi and pi prime be families isomorphic to each other over delta star. We define the log Shim degree as the following n+1 dimensional insertion number, which is very close to, which is very similar to Donaldson-Ohtake invariant. And if x0, d0, l0 is special K-stable, and pi prime are not isomorphic, then one of the Shim degree is structurally less than other Shim degree. This immediately shows our separateness for uniform adiabatic K-stable KT to trivial fibrations over curves. And next, adiabatic K-stability is simply a condition on the base curve. So we have to deal with the base condition. The base discriminant divisors. And so it is enough to show the following statement. I mean the correspondence T to max coefficient BT bar is conservative and upper semi-continuous, where BT bar is discriminant with respect to FT bar, where T bar is a geometric point. So this shows the delta invariant of the base curve is lower semi-continuous. So the rest is boundedness. And so to answer the second question, we want to bound the following with fixed N, U, V, the following data. I mean the FNUV is this set by taking a quotient by relative linear equivalence. I mean this forms from the this consists of the uniform adiabatic K-stable trivial fibrations over curves, dimension x equal to n, and we fix the eta volume or the anti-eta volume, and is a F1 polar bundle, only F1 polar bundle with a fixed fiber volume. So we want to bound them. And we show that, we introduce the following set, FNV W, for any W. We mean for any KFT trivial fibrations, where A is an ample and volume A is bounded from above with 4 conditions. Then there is a W, such as FNUV is bounded. This is easy by Bilkan theorem, but our technical point is this one. There is a natural forgettable functor, but this is subjective. We solved, and now we can construct the adiabatic moduli since we complete the 3 lefties. For negative u, we bound also the RKX is the product of a very ample line model for C for any F uniformly. Then we construct the following moduli for such R. Note that their reduced structure coincide. There is this stack, but it's tedious. We omit some conditions. But the point is that view R forms a separated dimorphism stack of finite type with a cos moduli space by K Mori. This is our main result. And we also constructed the module for positive U, the kappa x equal to 1 case. And furthermore, we deduced the following result by the module and the explicit criteria for uniform adiabatic stability. Consider FNUV, then there exists a uniform positive constant W, such that if volume A is bigger than W or equal to W, for any representative F, the XA is special case stable. But A is integral cohomology class. Anyway, so that the volume is uniformly bounded from below. So the uniformly close to the base. Then XA, all XA are automatically special case stable. In other words, by choosing A to be so, our adiabatic K moduli is certainly one of K moduli spaces. And furthermore, smooth members XA have CSK metrics simultaneously. And finally, I'd like to explain the partial result for cohesive projectivity. Let F be a Q-Gorenstein family of special K-stable pairs with maximal variation. If S is proper, then the sim line bundle. This is a chemically defined the line bundle, which is very closely related to sim degree. It is a sim degree is a degree of them. Anyway, under this condition, the sim line bundle is big enough. And by using this, we can show the analogous result to Fujiki-Schumacher. I mean, let MNV be the post modular space, and any proper subspace of it is projective. And finally, I mentioned that we preparing the upcoming work that for certain for certain moduli, we show the entirely quasi-projectivity. So I stop here. Thank you for attention.
Any questions?
So do you expect it has kind of like a certain version of compactification?
Compactification? I'm not sure. Since the for K semistability, the base of the K semistability of the base and the K semistability of the ambient space are not the same. So we have to classify.
Any questions?
I have questions. We have this criterion for special K-stability somewhere, like for different polarization. Did you apply it to some cases? How far from Fano can?
Far from Fano?
It's just
okay.
on the first few slides.
Okay. I'm not sure. It's I raised the examples of special K-stable ones, but they are all I know.
Okay.
And all of them. So counting this, so they're modular.
Any more questions?
So your moduli space has a morphism to the moduli space of curves, smooth curves?
It's a very good question. After that, we can discuss.
Okay.
So I'm wondering if you could have like a KSBA moduli related to what you have, because you can take a multi-section and add a small coefficient. This is what aH+L they consider. So if you can embed or relate this to KSBA, you have projectivity.
I'm not sure. Sorry.
What's the relation with the Dervan-Naumann moduli space of CSCK?
Okay.
What's the relation with the moduli space of CSCK manifolds of Dervan and Naumann?
Dervan-Naumann? With
I mean the relation between your moduli space and the moduli space of the CSCK?
So I mean, it's a simple reason. We assume YTD conjecture, so K-stability and CSCK metrics related. So is this answer?
Assuming the YTD conjecture, you can construct a morphism from your moduli to moduli space. You see?
Oh. I imagined so, but I'm not sure.
Any other questions? Let's just check the line. Okay, no questions. So let's thank the speaker again.